Welcome to a journey that transcends mere numbers. Today, we step into the architecture of the universe itself. We are embarking on a definitive series exploring calculus, the mathematical bridge between the static and the eternal flow of time. Before we dive into the ancient sands of Egypt and the fierce intellectual battlegrounds of the 17th century, a brief research disclaimer. While we strive for absolute historical and mathematical precision, the evolution of these ideas is a complex tapestry woven by many hands over millennia. We will cite primary sources and seminal texts throughout this journey to ensure clarity. Our goal is to move beyond the textbook and see the world through the lens of flux. Prepare to see reality not as a collection of objects, but as a symphony of continuous change. This is the origin of everything. Every grand edifice begins with a single stone. The very word calculus carries the weight of history in its syllables. It derives from the Latin term for a small pebble. In the ancient world, these humble stones were the first tools of computation, used in abaci and for counting sheep or grain. Imagine a merchant in a bustling forum, moving these pebbles to track the flow of commerce. This physical act of calculating eventually evolved into the most sophisticated mental framework ever devised by humanity. We moved from counting discrete physical objects, the pebbles, to measuring the infinite, the infinitesimal, and the ever-changing. It is a poetic irony that the math used to calculate the trajectory of a star or the curvature of a black hole shares its name with a simple rock found on a dusty path. To find the roots of this change, we must travel back nearly 4 millennia to the banks of the Nile. The ancient Egyptians were not just builders of pyramids, they were the first masters of spatial logic. In the Moscow Mathematical Papyrus, one of the oldest known mathematical texts, we find Problem 14, which demonstrates an astonishingly accurate method for calculating the volume of a frustum, a truncated pyramid. They didn't have the symbolic language of modern algebra, yet they possessed a geometric intuition that bordered on the miraculous. They understood that to measure the complex, you must break it down into the manageable. This was the first whisper of the method of exhaustion, a precursor to the integral. They were beginning to see that curves and slopes could be conquered if one had the patience to count the pieces. The intellectual torch passed from Egypt to Greece, specifically to Eudoxus of Cnidus. He formalized what we now call the method of exhaustion. This wasn't just a clever trick, it was a rigorous logical framework. Eudoxus realized that if you want to find the area of a circle, you can't measure the curve directly with a straight ruler. Instead, you exhaust the area by inscribing polygons within it. As you add more sides, moving from a square to an octagon to a hexadecagon, the gap between the polygon and the circle shrinks toward zero. This is the spiritual ancestor of the limit, the foundational concept of all calculus. Eudoxus proved that by narrowing the margin of error until it was smaller than any assignable magnitude, truth could be cornered. He was chasing the infinite through the finite. No one took the method of exhaustion further than Archimedes of Syracuse. In his seminal work on the sphere and cylinder, Archimedes achieved what was once thought impossible. He calculated the volume and surface area of a sphere. He viewed it as his greatest achievement, even requesting it be carved onto his tombstone. By imagining a sphere made of an infinite number of thin disks, Archimedes was performing integration nearly 2,000 years before the formalization of the integral. He wasn't just doing geometry, he was doing proto-calculus. His brilliance lay in his ability to see the sum of the parts as a way to define the whole. As noted in the Archimedes palimpsest, he even used mechanical principles, imagining the shapes on a scale, to find mathematical truths. He was a man out of time, waiting for the symbols to catch up. For centuries following the fall of Rome, the quest for the mathematics of change seemed to drift into a long, quiet hibernation in the West. While the method of exhaustion was preserved in the Islamic Golden Age and by Byzantine scholars, the European continent focused on static theology. However, beneath the surface, the seeds were germinating. Thinkers like Alhazen were developing early optics, requiring an understanding of curves, while Indian mathematicians like Bhaskara too were already touching upon the concept of the derivative to calculate planetary motion. This era wasn't a void. It was a slow cooker of intellectual history. The world was waiting for a bridge between the physical reality of motion and the abstract beauty of geometry. The small pebbles of the Romans were being polished by diverse cultures, preparing for a revolutionary leap. As the Renaissance dawned, the world began to move faster. Artists like Da Vinci weren't just painting, they were obsessing over the mechanics of water and the flight of birds. This required a new way of looking at time, not as a series of still frames, but as a continuous flow. The rediscovery of Greek texts, combined with a newfound obsession with motion, created a pressurized environment. If a cannonball travels in a curve, how do we find its exact speed at the peak of its flight? Geometry could describe the curve, but it couldn't describe the speed. The limitations of ancient math were becoming a literal bottleneck for progress. The stage was set for a radical shift from the what of shapes to the how of change. In the early 1600s, Bonaventura Cavalieri made a daring proposition. He suggested that a volume could be viewed as an infinite number of indivisible planes stacked together. Think of a loaf of bread. If you know the area of every infinitely thin slice, you know the volume of the whole loaf. This was Cavalieri's principle. While his peers criticized him for a lack of rigor, how can something with no thickness have area? Cavalieri was effectively hacking the system. He was moving away from the exhaustion method's tedious polygons and toward a more fluid, integrated approach. He was proving that the infinite wasn't something to be feared, but something to be utilized. He provided the slices that would eventually be summed by the first integral signs. Pierre de Fermat, a lawyer by trade and a mathematical genius by moonlight, took the next crucial step. He became obsessed with maxima and minima, the highest and lowest points of a curve. To find these, he developed a method to determine the tangent line at any given point. If you can find the slope of a hill at every single inch of your climb, you can predict exactly when you'll reach the summit. Fermat's work was the differential side of the coin. He was looking at the instantaneous, trying to freeze a moment of change to measure its direction. Though he didn't realize it yet, he was holding one half of the greatest secret in the history of mathematics. The tangent was the key to understanding the velocity of the universe. In 1665, the Great Plague of London forced a young student named Isaac Newton to retreat to his family home at Woolsthorpe Manor. In this forced isolation, his Annus Mirabilis, or Year of Wonders, Newton would change the world. Inspired by the fall of an apple and the motion of the moon, he realized that the same force governed both. But to prove it, he needed a math that didn't exist. He called his new invention the method of flux ions. To Newton, everything was flowing. A line was generated by a moving point, a surface by a moving line. He saw the world through the lens of physics and gravity. For Newton, calculus wasn't just a puzzle, it was the tool required to unlock the celestial mechanics of the heavens themselves. Newton's flux ions were deeply rooted in his obsession with motion and time. He used x dot to represent the rate of change, what we now call a derivative. His approach was intuitive but computationally dense. He was treating variables as fluents, things that flow, and their rates of change as flux ions. In his masterpiece, Philosophiae Naturalis Principia Mathematica, he used these concepts to lay down the laws of motion. While Newton was thinking like a physicist, Gottfried Wilhelm Leibniz was thinking like a philosopher and a linguist. In the 1670s, independently of Newton, Leibniz began his own search for a mathematics of the infinitesimal. He wasn't motivated by falling apples, but by the geometry of the infinite. Leibniz believed that if you had the right symbols, thinking would become as easy as calculating. He spent years obsessing over notation. He wanted a visual language that was so clear, the math would almost do itself. He saw the integral as a sum, represented by an elongated s for summa, and the differential as a tiny difference, or d. His approach was abstract, elegant, and designed for the masses. He wasn't just solving a problem, he was building a global standard. The brilliance of Leibniz lay in his symbols of integration and differentiation. These aren't just squiggles, they are a profound operational language. The dx represents an infinitely small change in x, and the integral sign represents the summation of those infinite parts. Unlike Newton's dots, which were difficult to use in complex fractions. Leibniz's notation allowed for the chain rule and multivariable calculus to feel natural. It was like moving from Roman numerals to Arabic numerals. It democratized the math. Even today, every student in every engineering lab on Earth uses Leibniz's script. He provided the UI, user interface, for the universe. While Newton gave us the engine, Leibniz gave us the steering wheel and the dashboard. The world finally had a way to talk about the infinite. Both Newton and Leibniz independently discovered the holy grail of math, the fundamental theorem of calculus. For centuries, finding areas, integration, and finding slopes, differentiation, were seen as two separate problems. The genius of the 17th century was the realization that they are inverses of each other. If you differentiate a function and then integrate it, you end up back where you started. It's like the relationship between addition and subtraction, but for the complex curves of reality. This connection is the heartbeat of calculus. It allows us to move back and forth between position and velocity, between total accumulation and instantaneous change. This realization didn't just solve a few geometry problems. It unified the physical world into a single, cohesive mathematical framework. Then came the fire. When Leibniz published his work in 1684, Newton, who had been using his method privately since 1666, was livid. The priority dispute began. It wasn't just a disagreement between two men. It became a full-blown international war of egos. The Royal Society of London, which Newton eventually presided over, accused Leibniz of plagiarism, claiming he had glimpsed Newton's letters and stolen the ideas. Leibniz defended his honor, pointing out that his methods and notations were entirely different. This calculus war divided the mathematical world for over a century. British mathematicians stayed loyal to Newton's flux ions, while continental Europe embraced Leibniz's notation. Sadly, Britain's loyalty to Newton actually slowed their mathematical progress, as Leibniz's system proved far superior for advanced discovery. In 1712, the Royal Society published a report called the Commercium Epistolicum, which officially investigated the claims of plagiarism. Unbeknownst to the public, Newton himself had secretly written much of the report that impartially found him to be the sole inventor. It was a dark moment in the history of science, a battle of titans that left Leibniz's reputation in tatters in England. Leibniz died in 1716, largely uncelebrated by the British establishment. Yet history has a way of balancing the scales. While Newton won the political battle of his time, Leibniz won the war of utility. As the 18th century progressed, it became undeniable. The language of change belonged to no single man, but the symbols used to speak it would be Leibniz's forever. With the foundations laid, the Leibnizian school took flight, led by the brilliant Bernoulli family. Jacob and Johann Bernoulli were Leibniz's greatest champions. They didn't just use his calculus, they weaponized it to solve unsolvable problems like the brachistochrone, the path of fastest descent. They turned calculus into a living, breathing discipline, applying it to everything from the vibration of strings to the paths of comets. Through their tireless work and correspondence, calculus spread like wildfire through the universities of Europe. They proved that this wasn't just a theoretical toy for philosophers, it was a practical tool for engineers, astronomers, and architects. The small pebbles were now being used to build the foundations of the modern industrial world. The revolution was no longer silent. In 1696, the first ever calculus textbook was published by the Marquis de l'Hôpital. Interestingly, l'Hôpital had hired Johann Bernoulli to teach him calculus and essentially bought the rights to Bernoulli's discoveries. Despite the questionable business arrangement, the book was a masterpiece of clarity. It introduced the world to L'Hôpital's rule for solving indeterminate limits, a staple of every calculus student's diet today. This textbook was a turning point. It took calculus out of the realm of private letters and into the public domain. It standardized the lessons, codified the rules, and made the infinitesimal accessible to anyone with a sharp mind. Calculus was no longer an occult art practiced by a few hermits in England or Germany. It was becoming the standard curriculum for the age of reason. If Newton and Leibniz were the architects of calculus, Leonhard Euler was its master builder. During the 18th century, Euler refined the language of mathematics into the form we recognize today. By introducing the notation for a function and popularizing universal mathematical constants, he provided the field with its modern vocabulary. He demonstrated that calculus could be applied to complex numbers and infinite series, transforming mathematics into a discipline as fluid and harmonious as music. Euler was the most prolific mathematician in history, authoring hundreds of papers, many completed while he was totally blind. He proved that calculus was not a static invention but a growing organic system. Under Euler's pen, the field shifted from pure geometry into analysis, becoming the most powerful predictive tool ever conceived. As the 18th century turned into the 19th, calculus left the chalkboard and entered the factory. The Industrial Revolution was powered by steam, but it was designed with calculus. To understand heat, pressure, and the efficiency of engines, scientists like Sadi Carnot used the tools of integration to measure work and energy. The language of change was now describing the transformation of thermal energy into mechanical motion. Without the ability to calculate rates of expansion and the curves of thermodynamic cycles, the modern world would have stalled before it began. Calculus was the invisible governor on the engines of progress, ensuring that every joule of energy was accounted for. We weren't just measuring nature anymore. We were beginning to master it. The true test of calculus came when science moved beyond things we could see. James Clerk Maxwell used vector calculus to unify electricity and magnetism into a single set of 4 equations. This was perhaps the greatest triumph of the language of change. Maxwell's equations showed that light itself was an electromagnetic wave moving at a constant speed. This discovery, rooted in the partial derivatives of calculus, paved the way for radio, television, and the internet. Calculus allowed us to see the invisible fields that permeate the vacuum of space. It proved that the universe wasn't just made of matter, but of fields and fluxes that could be described with perfect mathematical precision. The pebbles of the ancient world had finally evolved into the photons of the digital age. By the mid-1800s, calculus faced a midlife crisis. The infinitesimals, those tiny, ghost-like numbers, were still logically shaky. Skeptics like Bishop Berkeley called them the ghosts of departed quantities. To save calculus from a collapse of logic, Augustin Louis Cauchy and later Karl Weierstrass introduced the epsilon-delta definition of a limit. They replaced the intuitive flow with a rigorous, cold logic. They defined the limit not as a process of getting closer, but as a precise distance that could be narrowed to any degree of accuracy. This was the great formalization. It stripped away the mysticism of the 17th century and replaced it with a foundation of granite. Calculus was no longer just a brilliant intuition. It was a mathematically unassailable fortress. The language was finally complete. In the 20th century, calculus entered the strange world of the atom. Schrödinger used the wave equation, a complex differential equation, to describe the probability of where an electron might be. At the quantum level, everything is a wave of change. Calculus became the only way to navigate this landscape of uncertainty. It showed us that even at the smallest scales imaginable, where reality becomes fuzzy, the math remains precise. We use calculus to bridge the gap between the solid world of our senses and the probabilistic world of the subatomic. From the chemistry of our DNA to the transistors in your smartphone, quantum calculus is the silent observer, calculating the odds of existence itself. We had moved from counting stones to calculating the fabric of reality. While Schrödinger looked down, Albert Einstein looked up. To describe general relativity, Einstein needed a specialized form of calculus called tensor calculus. This math describes how space and time themselves curve and stretch in the presence of mass. Imagine the universe not as a flat stage, but as a trampoline that dips and sways. Calculus provides the math to calculate those curves. It tells us how light bends around a galaxy and how time slows down near a black hole. Einstein proved that the universe is the ultimate fluent, a four-dimensional manifold in a constant state of flux. Calculus is the only language flexible enough to describe a universe where straight lines are actually curves and now is a relative term. We were no longer just on the bridge. We were the bridge. But calculus also revealed a deeper mystery: chaos. In the 1960s, Edward Lorenz discovered that even simple differential equations could lead to wildly unpredictable results, the butterfly effect. Calculus taught us that while the laws of nature are deterministic, the future is often sensitive to the smallest change in the present. This gave birth to chaos theory. It showed us the limits of our own predictions while simultaneously giving us the tools to model complex systems like weather, stock markets, and heart rhythms. Calculus became the math of the unpredictably predictable. It taught us that change isn't always smooth. Sometimes it's a wild, turbulent ride. Even in chaos, there is an underlying mathematical order, a strange attractor, waiting to be mapped by the integral. Today, we don't always solve calculus with a pen and paper. We use numerical methods, algorithms that allow computers to perform billions of tiny additions and subtractions to simulate reality. When you see a CGI explosion in a movie or a structural analysis of a new skyscraper, you're seeing calculus in action. Computers use discrete calculus to approximate the continuous flow of the world. We have come full circle. We started with physical pebbles, moved to abstract symbols, and now we use silicon pebbles, bits of data, to recreate the universe in digital form. The language of change has been uploaded. We are now at a point where we can simulate entire climates or the birth of galaxies, all powered by the fundamental rules laid down by Newton and Leibniz. The latest frontier of calculus is artificial intelligence. At the heart of every large language model and image generator is an algorithm called backpropagation, which uses the chain rule of calculus to learn. By calculating the gradient, the direction of steepest descent, the AI adjusts its millions of parameters to minimize error. Every time an AI learns, it is essentially performing a massive, multidimensional calculus problem. We are using the math of change to create machines that can think and adapt. It is the ultimate irony. The math we invented to describe the motion of the planets is now being used to model the motion of human thought. We are teaching the language of change to our creations, hoping they might one day help us solve the problems we cannot. As we stand on the edge of the future, we realize that calculus is more than just a subject in school. It is the fundamental operating system of our civilization. From the ancient Egyptians measuring their fields to the engineers of the next Mars colony, the language of change is our most vital tool. It allows us to dream in the infinite and build in the finite. It reminds us that nothing is truly static. Everything is in a state of becoming. As we move forward into the next episodes of the series, remember that every symbol we use carries the legacy of those who dared to look at a pebble and see a star. The horizon of discovery is infinite, and calculus is the compass that will lead us there. We conclude our first chapter by reframing what calculus actually is. It is often taught as a series of hurdles, derivatives, integrals, chain rules. But in its purest form, calculus is the language of change. It is the grammar we use to describe a world in constant motion. When a car accelerates, when a virus spreads through a population, when a planet orbits a star, or when an AI processes a prompt, calculus is the silent engine beneath the hood. It allows us to take a snapshot of a single moment and understand the rate at which that moment is transforming into the next. It is the bridge between the now and the next. By mastering this language, we no longer see the world as a static picture, but as a dynamic, flowing process. We have moved from counting pebbles to measuring the very breadth of the universe. Thank you for joining us on this first excursion into the Calculus Chronicles. This journey through time from the Moscow papyrus to the desks of Newton and Leibniz is just the beginning. In our next episode, we will dive deep into the power rule and the mechanics of the derivative, stripping away the mystery to reveal the elegance within. If you found this historical and mathematical deep dive valuable, please consider subscribing and hitting the notification bell. It helps us continue producing high-quality, scientifically rigorous content for this community of thinkers. Check the description below for our full bibliography and recommended reading list, including The Calculus Wars by Jason Socrates Barty. We want to hear from you. Which historical mathematician do you find most fascinating? Let us know in the comments. Keep questioning and keep calculating.